Hello. So how are you? Hope you were able to see the previous episodes, which was dealing with thermodynamics and heat transfer. So we had performed 2D to 3D simulation, uh, steady state heat transfer, and that was under a few assumptions, very preliminary assumptions. We had found out the temperature of the source. We had found out the temperature distribution, how the structure is going to uh, convect the heat, I mean the temperature, okay, with the air blanket around it. And we also discussed that the system is going to be covered with a thin layer of air, and the convection process takes place apart from the conduction. So we saw the temperature distribution throughout the structure, and because of conduction as well as steady state convection. So the previous discussions, we concluded that the coming episode will be looking at how the heat transfer can be visualized. Okay, when we assume that there is an external distribution of air, say there is going to be a source, uh, I mean a wind source, or there is going to be a air source. We can assume that there is a fan, okay, and this particular fan is going to uh, throw out some amount of air, and that air is going to convect. So there is going to be a different medium, and from that medium there is air flow, and this air flow is going to reduce the temperature from the source. And we know that the source is the LED, and this LED is connected intact to the structure, and we also have the reflectors. So we can find out, I mean we can see, yeah, this is how the reflector, the internal region is consisting of the reflector, and this is the heat sink. So this projector lamp is going to be designed in such a way that it is not, I mean the heat sinks are not kept independent, instead it is merged with the projector lamp. So you know, this is one kind of optimal design where two different entities can be integrated. So the heat sink is integrated to the projector lamp system. Okay, so the design is robust, and it's a highly optimal design. We have arrived at the, the most optimal design, and we have also concluded that the particular thickness of the fins are also efficient in transferring the temperature evenly throughout the body. So here it is not only the conduction process, it is I mean apart from the conduction process there is a convection, it's a forced convection. So in the previous steady state thermodynamics simulation, we assumed that there is air is the medium, the fluid around the particular structure, the projector lamp, and that particular air is trying to reduce the temperature of the LED lamp. Okay, here in computational fluid dynamics, so here we are going to perform a CFD simulation, and we are going to find out, okay, how, because of how the air flow from the external source, it can be a fan and an exhaust fan, you can say an exhaust fan, and this particular exhaust fan is throwing out this much CFM of air, and that air goes and strikes the projector lamp, and that is cooling it. trying to cool it. So there is going to be a convection process, there is going to be a conduction process. So this conduction and convection is going to be a forced convection because there is a different source which is trying to remove the temperature. Okay, so now we don't have to model the external source. Okay, so we are instead going to specify a direction, and we are going to apply an airflow velocity of air across that particular direction, and then we'll define that there is an air which is flowing. Okay, now the third set of CFD simulation will be dealing with the modeling of the external source also. So which means the air that is going to be thrown out of the exhaust fan is also going to be modeled, and this particular CFD simulation will be considering it again as an external aerodynamics. Okay, external aerodynamics. However, okay, we will be able to understand the dynamics of the air which is flowing out of the exhaust fan, and it goes and strikes the projector lamp, and how the temperature distribution happens. I mean, how it is getting convected. So here, let us consider the same projector lamp that has got a head, and it has got the tail part. The tail part is integrated with the heat sink. Okay, and this heat sink is designed in such a way that it has got a fin. So now why this is appearing like this is we have applied a certain material properties. Okay, so now once we try to remove, when we can remove the material property for some time, so that the visualization will be proper. So let me remove the transparency so that, yeah, so yeah, this is how it's going to be looking like. So we'll be able to see the LED inside, we'll be able to see the reflecting surface inside. Okay, and we are able to see the heatsink, that is the integrated heatsink, the fins. Okay, because rendering is very important, because visualization can be really good if we have the proper rendering. Now, what we are trying to do is we are going to define the computational domain. The field of, I mean, the domain is nothing but the particular region of computation. So, was this an internal aerodynamics? Say, assuming that the system itself has got a conducting process, the fan, or there is some source to remove the temperature, an external convecting source to remove the temperature, and that is again integrated or embedded within this particular projector lamp, then that becomes an internal aerodynamics. So here the assumption is made that externally there is an airflow. Okay, so it's coming from some location. It's not coming from a particular source. We are not modeling the source. So instead it's coming out of a specific direction, and this particular direction can be modeled. Okay, so we are going to define the computational domain. So this is going to be the computational domain, and we can always think like who exactly is deciding the computational domain, or what exactly are the parameters that is going to decide the computational domain. Okay, now we have integrated. We have included certain things or certain parts into uh, this particular computational system. I mean, for the fluid dynamic simulation, we are going to incorporate everything. We need to understand the flow dynamics across the structure, and we need to even study like how exactly the system is going to behave, how exactly the system is going to behave uh, when there is an external influence. Okay, it can be a force, or it can be an airflow, or it can be an impact. Okay, any physical quantity, any kind of physical quantity, there can be some influence of that physical quantity onto the system. Now we need to decide how many, I mean, what systems are going to take part or participate in this particular influence. Okay, so here I want to study what is the airflow, okay, happening on the entire projector lamp. Okay, now see, there can be a particular uh, what do you call situation where we need to even identify the forces, the normal forces, the shear forces, okay, the mechanics, the dynamics of the structures. So here the structures are like we have the knuckle, and this knuckle is getting connected to the superstructure, that is the projector lamp. Okay, and it is connected using a bolt, nut and a bolt. Okay, now there is a airflow, okay, from a direction, and we also need to understand whether that particular airflow or the CFM of air is safe enough in a sense. It should not affect the structural integrity of the projector lamp. So that is what I am trying to do. The structural integrity of the projector lamp means the knuckle is connected to the projector lamp head using a nut and a bolt, and the air that is going to flow should not tilt to the direction, or it should not tilt to the angle in which it is inclined. The projector lamp is inclined onto the knuckle. Okay, when there is an excess flow of air, okay, there could be a possibility where the projector lamp can incline on that particular bolt axis. Okay, and we don't want that. So we can also try to understand like what should be the minimum CFM of airflow, okay, that comes out of the exhaust fan or the source, the external source, okay, so that the projector head remains at the same angle or the preferred angle or the desired angle, and doesn't go beyond, or it doesn't come below the preferred angle. Okay, so there are too many parameters. Okay, so now once we decide that we are just worried about the thermal distribution of uh, the heat which is generated from the LED bulb, okay, and we also need to understand like what would be the temperature distribution across the structure. So that is the point of interest. Now once the point of interest is only converged into this, okay, our studies can also be inclined into this. Okay, so here I am not going to consider the external structural mechanics, or the shear forces or the direct stresses that is going to come onto the knuckle or the bolt. Okay, so here the solid material that I am going to define for this particular bulb, the LED bulb, is quartz glass. I am defining that it's made of quartz glass, and I have also already like defined like what are the materials. So I am defining the material for uh, the heat sink, that is the fins, the projector tail, the projector lamp, the head part as well as the tail part. Okay, both of it is made of 1345 alloy. It's a aluminum alloy. Okay, I don't want to make it more cumbersome using a stainless steel surface, because cost is again a very important parameter. So cost is a parameter, the weight, bulkiness, but the bulk density is also going to be a parameter. So, and apart from that, the casting process, the machining processes involved in the manufacturing point of view. Okay, so we look out for a material that is very easy to be, I mean, that's more workable. Okay, and more ergonomical in nature. Okay, so aluminum is preferred, and this particular 1345 aluminum alloy is adopted for casting the entire structure and then machining. So there are two processes. Okay, so the top portion, the entire system, it can be casted from two different bodies, or the single body can be casted. Okay, that's one way of doing it. And the other way is to carve out the machining process. So with the machining process, the aluminum block can be completely machined using the EDM wire cutting methods, or you can also 3D print it. Today we have metal 3D printing where the desired shapes can be perfectly achieved. Okay, and the error is going to be, the error in, or the tolerances are going to be very tight. Okay, there is no anomaly that's going to be in the process. Okay, so any of these processes, the system can be done. Okay, and the cost is also going to be accordingly, because this will be, these kind of structures, they'll be manufacturing about 1 lakh, or 2 lakh, or 3 lakh, or 5 lakh pieces. Okay, and worldwide they sell it. Okay, for specific applications. Okay, now in such cases, they go for the cheapest and the most economical way of manufacturing processes. Okay, so now we have defined what are the materials involved in this, and we know that 1345 aluminum alloy is what is used for the structural part. Okay, and LED, we are assuming it as the quartz glass, and we have given the properties. So the material properties, uh, again, I want to emphasize that for structural simulations, the key parameters that we assign is Young's modulus, the modulus of elasticity, then we have the Poisson's ratio, then we have density, then we can also key in the shear, triaxial shear parameters, shear stress parameters. We can also define uh, the bulk modulus. Okay, so we can also define the strain portions. So when we choose non-material materials, or when we are performing a nonlinear simulation, so the material that we are going to give should also be accordingly. So now let's imagine that we are working on some polymers. Okay, so when we define the polymer, uh, the strain, okay, how it is going to behave uniaxially, biaxially, and triaxially, how it is going to get strained, and what are the stresses. Now experimental values are extracted, and these experimental values are keyed in or put inside the uh, mathematical modeling. Okay, and that is how we define the system, because the entire end of the day, the entire software has to be simulated or run using a computational device. Okay, it can be high performance computing machine, GPU. Okay, and there is a processor involved, so it can be 2 core, 5 core, 7 core, or 12 core, or 24 cores. So depending upon the speed, I mean the machine that we have, okay, and the kind of simulations that we are performing. Okay, so when we make use of these kind of hardware systems, okay, these softwares are pretty much capable to be run in these machines. So the machine will take the inputs that we are keying in from the software. Okay, and the software is going to define like how the physics is going to be applied to the structure, whether this is going to be a structural physics which is dealing with mechanics, or it is going to be thermal physics which is going to deal with thermostatics, or it is going to deal with thermodynamics. Okay, now the software will have that particular intelligence. Okay, based on the inputs we are keying in, and based on the material properties we are defining. So the software will be able to understand like what exactly is the kind of simulation that we are desiring. Okay, then it can understand. Okay, this particular input is keyed in, and when these inputs are keyed in, okay, this is the kind of simulation to be performed. So that will be a hydrodynamic, or it's a computational fluid dynamics. Okay, so the software is nothing but it's a set of coding. It's an algorithm. Okay, and based on those algorithms, the software is going to operate. I mean, it's going to function. And now, if it has to function, there should be a supporting device, and that supporting device is this computing device. Okay, so now we decide like what is the kind of computational device that we need to use. Okay, so now here it's a computational fluid dynamic system. So immediately the software will try to solve, it will try to bring in a set of the Stokes equation, okay, and then it will start manipulating the flow equations based on the inputs we are performing. We are going to give like what is going to be the airflow velocity, and based on that airflow, it is going to identify whether this is going to be an external aerodynamics. Okay, so now these are all the parameters we are going to give. Okay, we can find it here. So now I am getting into the computational domain, and I have decided these two parts. All these parts are going to be taking part in the simulation. Okay, so now we are going to assign the materials which we have already done. Okay, and then we are going to define the settings. So now we are going to say that this is a thermodynamic system, and this thermodynamic system is going to be driven by external flow conditions. So here I am considering the heat conduction in solid. Okay, so I am defining the software. So this is the software, and to the software I am keying in, and I am saying that this is a heat conduction in solid process. This is a thermodynamic process. There is a heat transfer involved, and this heat transfer is between, there is going to be a heat transfer or heat exchange between a solid and a fluid. Okay, so now, and I'm also going to define that there is going to be some thermal, this thermal phenomena is going to take place with respect to some time, delta T. Okay, so it's nothing but dq by dt. So the rate of change of heat with respect to time, that is dq by dt. Now we know that Q is equal to m into c into delta T. Q is nothing but quantity of heat generated in a system, or the quantity of heat eliminated from a system. That's the basic thermodynamic concept. And now Q is equal to mass multiplied by the specific heat into the change in temperature between the sink and the source. So from the source to the sink, when the temperature is, there is a change in temperature, there is a process. Okay, that process can be radiative, the process can be convective, the process can be conductive. Okay, these are all the processes, how it is getting transferred from the source to the sink. Okay, and we know from the source to the sink, when this temperature has to move, there is going to be a change in time, and that change in time is nothing but delta T. So dq by dt is what we are going to find out from this. So depending upon the time, so what is going to be the time frame, like how for the previous computational fluid dynamic process for a submarine, okay, we try to identify the hydrodynamic properties of the submarine. Okay, so now we define that the entire 25-meter submarine, it's an assumption. See, a submarine can be definitely, about some 100 meters or 200 meters or 250 meters, or some can be half a, 500 meters. Okay, so now we are taking a submarine which is 25 meters, and to that submarine we are going to perform a flow simulation, and we are assuming that it is embedded within a confined region, a computational domain of 1 kilometer. So, which means that the computational domain is 1 kilometer. So here the computational domain need not be 1 kilometer because the projector lamp itself is very small. Okay, so now instead of 1 kilometer, what I am saying, or I am defining the software, is my computational domain is going to be about 1 meter. Okay, and to this 1 meter, within this 1 meter, I am defining that this projector lamp is covered with a blanket of air. So that's how my computational system is defined. Okay, so to that 1 meter by 1 meter by 1 meter cube, okay, exactly the center 0, 0, 0 is where the projector lamp is going to be mounted. Okay, and I am trying to find out what is going to be the rate of heat transfer, what is going to be the change in temperature in this particular computational domain of 1 meter by 1 meter by 1 meter volume. Okay, so for a period of 10 seconds, so from 0 to 10 seconds, I want to find out, okay, what is going to be the change in temperature. Now the 0 to 10 seconds can be defined, say from 0 to 1, 1 to 2, 2 to 3, 3 to 4, so like that, 9 to 10. Okay, so each time can be defined as 1 second. Okay, but then the computational process is going to be very, very, very limited. It's going to be very small. Okay, so we won't be able to visualize that process. So what we are trying to do is we are going to again break the time by a factor of 0.01. So that is 1 by 100th of a second. So from 0 to 1, what is that? 1 second is going to be divided by 100. So that is 0.01. That's going to be my iteration time. So accordingly, 10, okay, 10 multiplied by 0.01. So that will be the total time domain. Okay, so that much iterations are going to be performed. So which means 10 divided by 0.01. So that will be 100 divided by 0.1, and that will be 1000 divided by 1. So 1000 divided by 1 is like, it's about 1000 iterations. A minimum of 1000 iterations is what we are going to perform. Okay, now let's define the fluid. So we know that this computational domain is going to be filled with air. So that I am trying to assume that the fluid is going to be air. Okay, why I am going to call it as a fluid is a fluid. What is a fluid? A fluid is nothing but it's a structure that is going to be filled completely within the shape. Okay, if it is a rectangular box, okay, it's a cuboid, the fluid is going to be fully filled. So the domains are going to be having some space. Okay, some space in a sense, if you consider a solid, the solid is going to be bound, okay, by one domain particle connected to the other domain particle. So the continuum, it's an infinite continuum. So every domain, every particle is going to be interconnected to one another. It's tightly packed, and that's the reason we call it as a solid. Now in the fluid, this packing of particles or domains are going to be lesser. So which means there is going to be a space, there is going to be a flexibility between the two particles. So which means the particles can vibrate, oscillate between each other. And that is the reason this flows. Okay, so that is one of the main reasons that depending upon this particle, okay, which is separated at a small distance Okay, it can be at a distance of say 1 micron, 0.001 at time t is equal to 5 seconds, and it can immediately become 0.01 at time t is equal to 6 seconds, and then at time t is equal to 7 seconds it can again become 0.1 and then again come back to 0.01. So this particular process of packing and unpacking or toughening and loosening will happen in case of fluids, and that is the reason we say the fluids. Okay, there are different kinds of fluids. We have compressible fluids, we have non-compressible or incompressible fluids. Okay, and it all depends on the packing. So how it is, mixed. Water is a homogeneous fluid. Okay, and it has got a hydrogen and oxygen. So it is 2H2O. So that's how this is going to exist. Now there is a hydrogen molecule and there is an oxygen molecule. The hydrogen and oxygen molecules, they fuse together, they come together. Okay, and there is going to be a state, a position where there is going to be a attraction and repulsion between the hydrogen and the oxygen molecules. And now this attraction and repulsion between the oxygen molecules and the hydrogen molecule is going to keep it stable, and that's the reason we call it's a stable fluid. Okay, now it is not going to be reactive. And when does it become reactive? It becomes reactive when one of the molecule is very badly in a situation to lose its electron, its outermost electrons. And when it is losing its outermost electron, it loses electron and becomes a positive ion plus. Okay, and after losing an electron, which is minus, this minus will again go and stick on to the positive. So that's how we have defined the fluids. Now these fluids can be mixable and it can be unmixable. In a sense, how much we try to mix it, it is going to again get separated, like oil and water. And this oil and water, okay, that has got different properties, the fluid dynamic properties. There is going to be surface tension for oil, and there is going to be surface tension for water. Okay, and there is going to be a viscosity for fluid, I mean the oil, and there is going to be a viscosity for water. And now we know that oil being less denser, it is going to float onto the denser fluid, which is water. Okay, and this oil is floating on the water, okay, with a thin film. There is a thin film of air, okay, that is trapping oil and the water, and that thin film is nothing but it's a surface tension. So that's the force of attraction and repulsion between the two layers, two different layers of fluids. Okay, oil is a fluid, water is a fluid, and between the two fluids there is going to be a force of attraction and repulsion, and that is because of adhesion and cohesion. So this adhesion and cohesion force, adhesion is nothing but sticking, cohesion is moving out. Okay, so this process, when these liquids are tried to mix, they are going to develop a state of viscosity. So which means the viscosity of these fluids will try to increase. Okay, it will be more like castor oil, more denser. Like castor oils are more denser, and these castor oil is mainly used for performing the experiments. You would have seen in the colleges they perform the experiment containing a huge tube, and this particular tube is filled with castor oil, and then there is going to be a lead ball or a steel ball which is dropped from a certain height, and this particular ball, okay, tries to move inside, okay, initially with the force of gravity, and after some point of time it's going to experience a kind of repulsive force, okay, because of the buoyancy processes. Buoyancy is again it is the basics for the flow dynamics, and because of this density, the castor oil density, is going to give a push onto the steel ball surface, and this again goes up, it tries to go up. Okay, so based on which we perform, this is the experiment for identifying the viscosity. Okay, pi p a raised to 4 by 8 eta L is what is the viscosity parameter. Okay, so now there is going to be the pressure, okay, which is going to be calibrated. A is going to be the radius of the steel ball, and based on that we are going to find out like what is going to be the system. So we have different kinds of fluids: non-Newtonian fluids, compressible fluids, and incompressible fluids. Okay, gases, etc. So here, though air is considered as a gas, here in this particular system we are going to consider it as a fluid. So we have considered air as the fluid, and then we are going to define what is going to be the solids. So the solid system is the external structure. The external structure is going to be solid, and that is also going to take part in the thermal process, the thermodynamic system, because we need to find out what is going to be the temperature distribution across the projector lamp. Okay, so the thickness matters. If you try to slice it along xy or yz or zx plane, okay, we are trying to find out what would be the temperature distribution across the thickness. So we are considering the structures, the knuckle structure, the bolt, nut, the projector headlamp, everything is going to be a part of it. Okay. So once we have defined, we are going to say like there is going to be a particular velocity of air which is going to come from some source. We are not going to define the source here in this simulation. That we can probably see in the next episode, where I'm going to mount an exhaust fan nearby at some particular distance, and I'm going to throw air out of that exhaust fan. Okay, now let's say about some 50 cfm or say about 60 cfm of air is going to be sprayed onto this particular or thrown onto the projector lamp, and how that airflow is going to wipe out the temperature from the system, and it's going to radiate it to the atmosphere. So that will be the next simulation. So here I am defining that the velocity parameters, the velocity is about 5 meter per second. The 5 meter per second is the negative x-axis. So here this is my projector lamp, and the projector lamp is going to be so the inline axis, is the axis in which the LED bulb is mounted, so that is Z, okay, Z, and then here the vertical is Y, and then we have the horizontal again X. Now let me assume that in the X direction I am throwing out an air of 5 meter per second. Okay, so here I am applying a negative symbol. The reason because it's in the backward axis. So X is on this axis, the positive number line. So I am trying to give it on the negative number line. Okay, so now once I have defined this, I am going to define. I can define like what exactly is the way that the temperature can yes. So this is the velocity, and this velocity can depend on certain time. Okay, at time t is equal to 0 seconds, what is going to be the temperature? Say we just mentioned that this particular LED, which is made of quartz glass, that has got a specific resistance, it has got a thermal conductivity. Okay, and then we are defining that the temperature of this particular LED bulb is going to be this much. Okay, so I assume like it is about, say, about 180 degrees. Okay, so it's not 180, it can go beyond, okay, depending upon the kind of LED, the bulb that we are using for a application. If it is a floodlight, okay, which is going to be used for surveillance purpose, okay, which can throw light almost for a kilometer. Okay, when we use an LED bulb of that kind, the temperature inside the LED that's going to be generated is going to be about 1200 degrees or 1300 degrees. And now that particular kind of light or that particular kind of temperature is what is uh, you know exhibited by that LED, because it is again depending upon the optical illumination capacity, how much it can illuminate. Okay, so the requirement is like there is a ground which is about 1 kilometer, and there are supposed to be four floodlights which is to be mounted in the opposite directions, one onto the east, west, north, and south. Four different floodlights in diametrically opposite regions are to be installed. Okay, so for that, covering that 1 kilometer of stadium, okay, the range is calculated, okay, based on the optical calculations. So a certain method is used for calculating the illumination capability, and from the illumination capability they try to find out like what is the range in which that particular light can be spread. Okay, so we have some softwares that can do like Spios, okay, and Zimax. uh, so there are few softwares which is especially used for lighting purposes, where that particular light using photo ray tracing method or any other methods. It can be even finite element methods and or boundary element methods. Okay, that's again a very interesting method with which the optical intensity can be calculated. And now for this optical intensity, there is a process where we can reverse calculate the temperature. What is going to be the temperature of that particular source? Okay, so now we have understood like what is going to be the temperature, and that temperature is what we are going to give, okay, for the LED bulb here. Okay, we don't have to perform a optical simulation to find out that. Instead, we are defining this particular projector lamp is going to be used for this application, and the illumination capability I is going to be this, and when the illumination capability is this, the temperature is going to be this. Okay, so now we have arrived at that temperature. We are giving that as the input. Now we define like what is going to be the temperature and how the temperature is going to vary with respect to time. And we have defined that for this particular computational domain of 1 meter by 1 meter by 1 meter for 10 seconds. Okay, so now time t is equal to 0, what is going to be the temperature? At time t is equal to 1 second, what is going to be the change in temperature? So we are defining it. So we define it in such a way that we are going to gradually increase it. Now from 0 to 1 second, 1 to 2 seconds, 2 to 3 seconds, it's going to increase, and from 3 seconds it's going to rapidly shoot. Okay, the temperature is going to abruptly increase, and the temperature change, the rate of change of temperature, okay, from 3 seconds to 5 seconds, the temperature is increased by 2 times. So which means when time t is equal to 0, the temperature is the the actual temperature of the LED, say let us say 180 degrees, and when time t is equal to 2 seconds, that 180 becomes, say it's going to further reduce, and then time 3 is equal to 3 seconds, it's going to again reduce. Time t is equal to 4 seconds, the temperature will reduce drastically. So that's what I am trying to mean. So there is going to be a transient curve that I am going to impart for this particular simulation. Okay, and I have defined the transient parameters, the time dependent parameters. Okay, once I am done with it, then I perform a simulation. So here I am defining the solid material, that is the LED, as the quartz glass. So here you will find the blue region that I defined. So yeah, this is the blue region, quartz. So now we know like what are the properties of quartz. So quartz, let's say the properties are it has got a thermal conductivity of 1.4 watts per meter Kelvin. Okay, and then we have a temperature of 1956.15 Kelvin. Okay, so now we need to convert from Kelvin to degree Celsius. Okay, so here the temperature is given as Kelvin, and this Kelvin will be converted into degree Celsius once we perform the simulation. Okay, so now the density is 2200, the specific heat is 670 joules per kg per Kelvin. Now these are all the input parameters that is to be defined for the bulb that we are using, because that's the temperature source. Okay, so now based on that, we are performing simulation, and we are defining, like, these are all the the outputs that I need. So the first output is, I am saying, like, if there is a heat and mass transfer involved. Okay, so we know that there is going to be a heat transfer involved, because the outer cover, that is the projector lamp and the knuckle and the nut bolt and everything, is going to be metal based. It's an alloy. Okay, so that is a certain that has got a certain thermal conductivity, specific heat, everything, density, etc. Okay, so now there is going to be a heat transfer for sure. Now, because of that temperature, is there any material which is going to radiate off, or whether it's going to flow off? Okay, so instead of using aluminum alloy, if I try to use a metal or an alloy which is very low in modulus of elasticity, say the Young's modulus of that is very less. Okay, because of this particular temperature, which is 1900 Kelvin, there is a probability that metal can flow, or the alloy can flow. Okay, if it flows, then there is going to be certainly a change in mass. Okay, so that means there is going to be a heat and a mass transfer simultaneously. So here, this particular problem, I have a doubt. I just need to understand whether there is a change in mass. I don't know. So for that, I am giving that, okay, I need to understand what is the mass of the fluid and what is the mass flow rate. Okay, so these two parameters I have defined, and then the volume flow rate also is defined, and I need to find out what is the velocity, because I say that there is a 5 meter per second of air along the x-axis that is going to blush onto this particular projector lamp, and during that blush, okay, there is going to be some temperature which is going to be removed out of the projector lamp through the convection process. Now I need to understand, like, I am defining what is the heat transfer coefficient. Okay, so now the average heat transfer coefficient is what I need to understand. That is very important, because I say that air is going to be acting as a fluid in this particular domain, and air has got a certain coefficient, convection coefficient. Okay, so every fluid has got a convection coefficient, and that is again the experimentally calibrated values, and these values are keyed in, and we are trying to find out the heat transfer coefficient also. Then we are trying to find out the heat flux, okay, and what is going to be the surface heat flux, convective, because of the fluid convection, and then any wall temperature, if any, and then the heat transfer rate of heat transfer, that is delta T, is what we are going to find out. Okay, so now I'm going to define the process. The process is going to be a finite volume system. We are going to break the entire computational domain. So this is the computational domain. Okay, and this computational domain is going to be broken into individual cells, and I am going to define either cuboid or whether rectangular, okay, kind of cells. Okay, each cell can be same size, or the cells can be varying also, and at junctions, at certain regions where I want to find out the temperature across the thickness, or at some junctions I need to refine, so I adopt a narrow channel refinement process, which means within the software there is an intelligence in which I am trying to define that this particular boundary or this particular cell has to be further discretized into, say, about 10 times you need to discretize. So let us say one cell, one cubical cell, okay, is like 1 unit by 1 unit by 1 unit. Now when I perform a narrow channel refinement, this particular cube of 1 by 1 by 1 is going to be broken 100 times. So that's how it is refined. So it is nothing but, as I told you in the case of finite elements, where the nodes are going to be the interpolated points. So in between the nodes, so let us say a tetrahedron, it has got a 4 node, okay, and now in between the 4 node, on each surface, the centroid of the surface, we are going to identify what is going to be the value, the physical value, whether it's a strain or stress or temperature, It's like the Gaussian integration. The Gaussian integration says that within a space, okay, there is going to be an infinite boundary. Space is an infinite boundary, and it can be integrated from 0 to the value n. So 0 to 1, there is a integration, and then from 1 to 2, 2 to 3, 3 to n. Okay, so we have these many integrations piled up. So every layer of the solid block is sliced, okay, with a unit thickness, and within this unit thickness we are identifying what are the parameters. Okay, so now that is integrated. It's called as the volume integral. Okay, so on one slice, on one plane, xy plane, it is going to be a surface integral. Okay, and that when projected with one unit, that becomes a volume. And that's the Gaussian integration or the volume integration. So within that volume, okay, we are trying to refine. That refine is nothing but it's called as the interpolation in finite elements. Okay, so now all these parameters are put in. Let me show you the mesh. So this is how the mesh is going to look like. Okay, so this is only a representation. Okay, so there is one plane xy, yz, zx. All the three is going to be like this. And once we perform the simulation, okay, the simulation will be performed onto the entire big, this complete computational domain. So with the mesh, what you see in each plane is going to get integrated over that particular volume. That's what I mean. Okay, so it's very simple to understand the logic. On each plane we have got the meshing, and this mesh, okay, each cell, each rectangle, whatever you see here on each plane, that is going to get integrated over the next dimension, that is the thickness. Okay, now once the complete meshing is done, we perform the simulation. Okay, so now once we perform the simulation, we'll be able to find out the parameters what we wanted to determine. So this particular simulation can take some time because it's again a time domain based system, that is transient system. So in time domain, okay, so there is going to be a lot of equations that it needs to calculate because it's a fluid dynamic process. Okay, it is going to be considering the basic Stokes equation, and then it is going to find out the thermal flow equations. Okay, now comparing the thermal flow equations and the flow equations, that is the hydrodynamic equations, and these flow equations are going to be compared. Okay, and then the process is going to be yes, the process is going to be performed. Okay, so now what I'm trying to do is I've run the simulation. Okay, and when I run the simulation, I'll be able to find out like what is going to be the system, how the process is going to consider the flow equations, and what would be the computation time and what would be the average iteration time. All these things can be based on that. So I have already performed the simulation. Okay, so let me unload the simulation. Okay, and then let me run the simulation once again so that we'll be able to better view the system. So now I'm going to calculate, okay, and I'm going to consider this, the domain, everything is put, the inputs are all keyed in, and now we need to perform. So what I'm doing is I can add computers to this, because if this is going to be a very complex CFD process, okay, where I need to understand the vortex studies, okay, and the vibrations created because of the vortex. Say, for example, when the plane is flying at a certain altitude, and then it is going to experience a turbulence, or it gets into any air pockets, there is going to be a lot of vortexes or eddies which is going to be created, and because of these vortex, the structure can vibrate. There can be a flutter. Okay, and that vibration needs to be accounted for, where the computation becomes a very complex process. Okay, so for which I need to get into parallel computing. So parallel computing, I can integrate many. So here I am using a laptop. Okay, and this particular laptop has got a 12 core system. Okay, and then this has got a 16 GB RAM in it. Now, for performing such complex task of vortex-induced vibrations in the ocean, okay, when the ship, is moving at say some 50, 60 knots or maybe about 80 knots, it goes and strikes on an iceberg, and then there is going to be a huge impact, and that impact load is going to be, transferred into shock loads and vibrations, and then because of those vibrations there are going to be a lot of dynamic changes. Okay, so now in order to study those kind of critical complex systems, we go for parallel processing. So there I can add my computers, add my system. Now I'm having about 12 cores here, and I'm making use of all my 12 cores, and then I run the simulation. So once I run the simulation, I'll be able to identify, I'll be able to find out what are my goals. So now here, uh, let me try to find out the goals. So yeah, this is how the goals are defined, and this is how the convergence can be identified, monitored. So I have the parameters. I have here is heat flux, heat transfer coefficient, average heat flux convective, then velocity, temperature, heat transfer rate, and mass transfer rate. And here there is no flow rate, okay, because that mass is not flowing, which means the mass is isotropic and it is still alive. It is within the linear system. Okay, there is no flow induced, or there is no non-linearity which is coming. So what I do is I remove the particular flow rate and the volume rate. Okay, then I try to find out like what is the heat flux. So this is the computation process, and during the computation process I am able to find out what is going to be the temperature, wall temperature, what is the average velocity. I am able to find out what is the heat transfer rate, and I am able to find out what is the mass transfer process also. So it is about 0.0128 kg of mass. Mass is like the air fluid. Okay, that much fluid is going to be thrown, and it is going to find out. So here what I am doing is I am trying to find out what is the pressure or temperature, okay, of the system. So yeah, we are able to find out like when the process, the computation is happening, when the computation is going on, I am able to find out what is the flow. So here I am trying to find out what is the temperature. So you find that the temperature is about 1201.54. Okay, that's the maximum temperature, and that temperature is arising from the lamp, that is the LED lamp. Okay, and now because of the forced convection, there is a airflow across the x-axis, and because of that airflow, there is going to be a heat transfer. Okay, there is no mass transfer that is defined. That is already understood. Okay, and that's the reason we removed the volume and the mass flow rates. So we know that there is no mass transfer. So there is a heat transfer involved. And what is the rate of heat transfer? That is what we have to find out. So here we are able to find out what is the temperature, the external temperature. So the entire computational domain we find blue, which is about 18 degrees. Okay, and now within that particular projector lab, across the projector lab, we are able to find out the other temperatures. So inside the area where the curvature, the projector headland inward curvature is there, we find that the temperature is lesser, Okay, and red, what you see is the temperature of that particular projector lamp, you know, uh, structure. Okay, so now we can find out like what is the uh, pressure. If at all there is a change in pressure, let's say what is the pressure change. So it is nothing much because we are able to find out zero point 0.9 atmosphere and 1 atmosphere. There is no much difference. And now let's try to find out the velocity. Yeah, so this is the velocity. So the region in red we are able to find it is about 7.5 meter per second. See, this is the rate of change of heat transfer, how the heat is getting transferred because of the airflow. Air flows and it's cooling down the system. Okay, so now this is the velocity plot, and this velocity plot shows that still the temperature, I mean the airflow inside the chamber, the projector head lamp chamber, the velocity is about 0, and across the, around that particular projector lamp, we are able to find that the velocity is about say 5, 6, etc. Okay, so which means there is going to be a good amount of heat getting transferred within the system. Okay, so now once the computation process is completed, we are able to find, yeah, this is the uh, the goal plot. There should be a convergence scheme. It's starting from the higher range, and from the higher range everything is coming down. Okay, you can see that computation is still going on. Okay, so it is trying to bring all the other areas, the heat flux, the heat transfer, the velocity, then the heat transfer and mass are all converged. It has all converged, and now there is only one parameter that is trying to converge, that is the temperature. So it is still at 1171, and let's see how many iterations. So the total number of iterations here, now what we have seen is about 620 iterations. Okay, so it's still trying to perform. So 450th iteration, the temperature convergence achieved is about 1170. So it has to still converge. Okay, we saw it is 1900 degrees, and 1900 degrees has dropped down to 1900 Kelvin. 1900 Kelvin is getting dropped to about 1170. Okay, so now let's try to say how many iterations have passed. So here we know that, yeah, there is the iteration, 500 iterations are completed. So 500 iterations, the solver has completed solving the process, which means that everything has converged, has come down. Okay, so now let's try to see how the system, the temperature looks. This is the velocity plot, and now let's get into the system. And okay, so now what we are trying to do is we have defined the time, and we have defined that 10 seconds is the maximum. So 0 to 10 seconds, this 10 seconds is going to be broken into 1 by 100, so that is 0.01, and 0.01 to say about 10 seconds is going to take about 1000 iterations. So we have seen that at 500 iterations, the goal is converged. Everything is converged. Okay, so now let's see what is going to be the system. Yeah, so this is going to be the temperature. Okay, so yeah, so we have the headlamp, the projector lamp, and the projector lamp is going to yeah, it's going to be covered with the velocity. So now this is how the velocity plot is. The air flows, so we are able to see the airflow, and this airflow is seen on the central axis. Okay, so across that particular, now let's remove this, and let's say that it's going to be exactly divided into half. Okay, so here we are able to find out. Yeah, this is how the temperature I mean the velocity is going to be, the air flow is going to get within the system. So now let's see what is the change in temperature. So now the temperature of the system, yeah, this is how the temperature is going to be. So we have 1200 degrees. So 1200 degree is the structure's temperature, and that 1200 degrees is going to be uh, reduced. So externally, whatever heat is getting dissipated, we are able to find out the temperature. So it's about blue here. So which means the person, okay, standing behind it is going to experience a temperature, a heat. So how big is that heat in quantity? It's about 150 degrees. So 150 degrees at some distance. And now let's try to find out at what distance the temperature will be reduced. Okay, so that is the main reasons these projector lamps or flood lamps and all those things, they are kept at a distance which is completely away from the environment. Okay, so that there is no thermal radiations, okay, from the system generated. Okay, so now let's find out the fluid conductivity. So this is the fluid conductivity. The fluid conductivity. Air is going to be again a conductor. Okay, that's the reason I said that air is considered to be a fluid here, and fluid is supposed to be a conductor. I mean, here in this particular case, it's a good thermal conductor. It's going to remove heat. So that's the reason. That is the reason we call it as a the conductor. That's the reason it's used for eliminating heat, the temperature. Okay, so now this is the the fluid thermal conductivity. So it is between 0.02 and 0.09. Okay, so there is a change. Okay, now let's try to find out uh, is there any noise generated? There's going to be a very minimal noise, a very small noise, and it's not even going to be about not even say 50 hertz or say about 100 hertz. It's not going to be even the low frequency noise. Okay, so now let's see what is going to be the turbulent energy. Okay, so the turbulent energy is going to be this much. And now, is there any stagnation density? Yes. So definitely there is a stagnation density, and which this is showing that the air is getting trapped and it is very well convecting the projector lamp. It is trying to convect. The air is trying to convert the projector lamp. So this is the flow. The air is mixing with the temperature and trying to remove that. That is what we see here. Okay, so now what we do is let's try to quickly find out the other parameters. The see, there are two ways of looking at the system. So one is by the graphical process where we have plots and simulations, etc. And the other one is going to be a graphical representation. So where we have the the x, y, z axis, and we can also see how the parameters are going to vary with respect to the axis. So here let's start from the pressure. Okay, so this is the pressure flow. Okay, so now we have plotted the goals also, and we'll be able to find out how the goal is going to. Yes, so let's have it here. Okay, so now you are going to find out what is going to be the average mass. So this is the mass change, the fluid mass. Okay, so it is 0.014 kgs and 500 iterations, so it's coming down, and it's going to be somewhere about 0.012 or 0.013. Okay, so the change in mass is only very small. Okay, it's negligible quantity. Okay, maybe about a gram or say up to 5 grams of change. Okay, so now let's try to find out what is the average velocity. Yeah, this is the velocity plot. Okay, so the velocity plot, the convergence is happening exactly at 403. 403, the system ceased. I mean, not ceasing, the system stopped. The calculation stopped, the convergence occurred, and we have found out the solution. Okay, so now this is the pressure. Now let's see what is the temperature. So the temperature you will find, this is how the temperature is going to change. Okay, there is going to be a drastic change. Okay, it is going to increase, then finally it is going to drop, and then again it will increase, then again. See, what we are trying to find here is this change, the big, dip, and dip in this particular plot is because, you are able to find the staggered, so, graph here. The reason because uh, there is going to be a convection induced and the air is trying to suddenly cool down that particular part of the system, and that's the reason the temperature is dropping down, and then again it is trying to increase. So the calculations, at various stages of the calculations, we are trying to see that uh, the solver is trying to converge. Okay, solver is trying to converge, but still again there are some parameters which is inducing, and it will again shift the convergence rate, and then again it comes down. Okay, so that's the reason we find this particular staggeredness. Okay, now let's find out what is the heat transfer coefficient. Okay, so this is how the heat transfer coefficient is, and we can find what is the heat flux, which is very important. Flux is very important. So here again we will have to, let's find out what is going to be the, so let's see what are the other parameters here. Okay, so electricity, so dynamic pressure. Dynamic pressure is again going to be the same pressure, that's the relative pressure. And then we have found out what is the fluid. Uh, Now density of the fluid. Okay, and then we have any vorticity. Vorticity. So this is the vorticity. So there is no vortex because it's a thermal simulation. Okay, we can't expect any kind of vortex or it is because there is no mechanical vibrations happening. Okay, so now we have found out this. The temperature of the fluid. Okay. Temperature of the fluid is nothing but the air. Temperature of the air. So this is how the air is binding or bounding that particular projector lamp. Okay. So now here the heat flux is found out, and the conductive heat flux, and this is the wall temperature. How it is going to increase. It's going to increase, and then suddenly start dropping. It will come, and at a point 1171 degrees, it is converged. Okay, so now here this is the temperature, and now okay, and as I told you, there is no shear stress or anything like that. Okay, because there is no mechanical forces. Okay, so now let's try to find out what is going to be the surface heat flux. Yes, so this is again, it's a thermodynamic factor. So this is again going to be the inverse of the temperature. Okay, so yes, the heat transfer rate, which is again a very important. This is how the heat transfer happens. So time, okay, at what time, what is the temperature, and how many iterations. Okay, so now with this, let's conclude the process. I mean the episode. And as I told you, like one single problem can be looked at from different perspectives, and we have seen the second way of looking at it. The third way of looking at it is the actual, I mean, the complete, the complex system where I told you this particular airflow can be modeled and it can be shown as if it's thrown out of a system, an exhaust fan, okay, and that goes and strikes this particular projector lamp and how it takes the heat or removes the heat away. Okay, so we will see that in the next episode, and let me once again conclude by saying that please subscribe and share this particular episodes, whatever you see here, because this is very, very interesting and important for every engineers. Okay, no matter structural engineer or fluid dynamic engineer or thermodynamic engineer, any kind of engineers, they need to understand the mechanics. Okay, as I told you, it can be mechanical, I mean the structural mechanics, it can be thermodynamics, it can be hydrodynamics, it can be electrostatics. Okay, we have all kinds of physics, that's why we call it as multi-physics. Okay, and now it's not knowing the physics, it's knowing the physics the right way and try to implement it, how to use it in a problem. Okay, that's the most important challenge. Okay, and once we understand the theory, and once we also understand how it is practically being executed, then solving every problem becomes, very simple. Okay, it's not complex at all. The only thing is there should be some understanding. A domain understanding is very important. If you understand what is structural mechanics, you need to know what is statics, what is dynamics. You need to know all laws of motion. You need to know what is friction. You need to know what is static friction. You must know what is a rolling friction, what is a kinetic friction. You know what is. You should be knowing what is a viscosity, what is a buoyancy. You need to know what is surface tension. So these kind of domain knowledge is very important. And once you have the right domain knowledge and you identify what is going to be the physics that you are going to adopt to solve the problem, okay, the tool is never a problem. You can always go and learn tool somewhere. Okay, it can be Nastran, or it can be ANSYS or Abacus, or it can be CFX, it can be Fluent, or it can be Flow. Any tools. It can also be acoustics tools like Virtual Lab, LMS Virtual Lab, Sysnoise or DADS, or it can be any kind of tool, MATLAB or Simulink. Okay, any vehicle dynamic tools, any tools used for a specific purpose application. Okay, so tool is not going to make a difference because every tool is structured and it's coded properly with the proper domain knowledge. The domain doesn't vary. Okay, if one company, if ANSYS is doing, is making an algorithm for hydrodynamics, okay, the algorithm made by Hexagon or the algorithm made by Dassault system will also be the same. The domain knowledge is, as long as the domain remains the same, the tools are going to be the same. The process involved in the tools, the algorithms, okay, everything is going to be the same. The only thing is that there will be a change in the graphical user interface. That's it. Okay. Apart from that, there should be a proper domain knowledge, and you should know what is what, and you should be knowing how it is going to be applied. Okay, so thank you very much for this particular patience trying to understand the problem. Okay, let's try to make it more interactive in the next session, where it's going to be a forced convection process, where we will identify an exhaust fan that can blow out a certain CFM of air, and how that air flow is going to cool down the entire system. Okay, so kindly subscribe and share to all your friends, your colleagues. Okay, so we can also plan for interactive discussions or sessions. Okay, so please feel free to always raise your query. Your comments are always welcome. Okay, thank you very much.